All right, well, welcome everyone. I'm Greg with AWS, and joining me for today's session is Shruti, also from AWS, and then Clay from JobCase will be going through a case study. So in terms of the agenda, we want to talk about democratizing access to data. I'm going to set up a little bit about some new features from AWS and kind of the AWS perspective about making data available for analysis. And then Shruti is going to go through a demonstration. It'll run about 10 minutes or so to kind of show some of the new features and how we can empower the consumers of this data to get access to more data in an easier fashion. And then after that, Clay is going to talk about an actual application, how JobCase was able to take the concept of democratizing access to data and lessons they learned as well. So it's a little bit of a theory up front, then a demonstration, and then a practical application of putting democratizing data into action. And we'll take questions at the end as well. So this topic of I guess the different term, but democratizing access to data, what it really just comes down to is how do I get more individuals inside my organization, partners, third parties, customers, access to data so they can have better insights, better decision making. And in the past, these analytic systems were very expensive, they were constrained by number of users. And so we had to be really careful about who we gave access to data, like who got access to the reports, what were the logons to the database. And today we think about this world where we want to improve operational efficiencies, we want to be able to make informed decisions and accelerate innovation. But really it's about empowering every individual in the organization, internal, external, with the right data. And then what is the cloud native architecture to support both the number of users as well as simplified interfaces to be able to get access to that data. But you think about what are some of the challenges? Like I think everyone conceptually says, yeah, we want to give access to more users. So this term we're using, democratizing access to data. But these are some of the barriers and blockers we've seen. The first is just around, okay, how do I know where the data is at? It's in many different sources. It could be in Salesforce, so a SaaS application. It could be an on-premise database. It could be in all these different areas. Then we need to be able to assemble that data for analysis, right? And build data pipelines to help with data transformation. And we find a lot of times is that, yeah, that makes sense, but then we end up with data in different silos, right? So I have my data lake, my data warehouse, perhaps different data warehouses based upon different business units. And it's hard to kind of collaborate on that data. But then also thinking about, even if I am in AWS and using services like Redshift for data warehousing, I have to think about, okay, what's the instance type? Am I on the latest generation, older generation? Do I have enough instances for data pipelines? What do those look like? As well as this need to kind of think more about predictive nature of analytics. And finding data scientist skills can be really challenging in today's market, right? So how can we be able to make the power of machine learning available to a broader set of users who might just be familiar with SQL language, right? And then also knowing that it's not just about a report or a dashboard, but oftentimes data is shared with other systems, right? I might be looking at third-party data sets for ingesting and then being able to then expose the data to other systems as well. It could be application data, could be shared systematically or programmatically with my partners, right? And then just thinking about, okay, well, at the end of the day, I have a data analyst, so I'm not giving the data to an application, but to a person. And this challenge of sifting through dashboards and reports and where is the metric at, as opposed to just being able to ask questions of the data. And so this kind of is a quick summary of just thinking about what are all the different ways that inhibit access to data, which then limits how we use this term democratizing access to the data. And so today we think about, from AWS, this idea of easy analytics for everyone. And thinking about the different personas, the data engineer, the developer, the business user who needs to get access to the data. And so it seems pretty straightforward but now today in the cloud, and particularly using cloud native services, how do we just automate everything? How do we create this factory of data products? And thinking about moving to a world with serverless everywhere. So from data ingestion, analysis, visualization, not having to think about an EC2 instance type at all, right? So I want to think about using analytics as a service in a serverless service, right? And then being able to visualize the data. And oftentimes you think about visualizing it in terms of a dashboard or report, but you might have a notebook. You might have an analyst that wants to write a SQL query. And you don't want to have to install and configure a bunch of different tools to be able to get access to data. So thinking about what's the way that that consumer of data wants to look at the data. It could be a dashboard, it could be a report, or it could be a question, right? And then also this idea of creating a data factory really comes down to removing the administrative tasks. So if a business user has a question, we don't want to have to go back to the DBA team to prepare the data, to apply some kind of special customization just to get the performance. We want to leverage sort of the automation of the cloud and of AWS to be able to help prepare the data and the internal data structures, where we think about the basic idea of loading data, querying data, and then adding more users, right? And adding more users shouldn't mean having to go back and reconfigure. And this is oftentimes driven by a lot of the new serverless architectures that we announced and talked about this morning, including Redshift serverless as kind of at the core. And how this looks, we want to think about, hopefully not too overly complex depiction, but putting the consumers of the data or the users of data at the center, and thinking about from a data analyst perspective, do they need a SQL interface, right? So in Amazon Redshift, we now have a query editor, which is the native part of Redshift, where you can write a query, share queries, be able to interact with the data without having to configure, again, the third-party tools to be able to do that. But then also from a business intelligence perspective, thinking about BI tools like Amazon QuickSight to be able to visualize the data and ask questions of it. But then also leveraging the rich API of Amazon Redshift to be able to write some kind of application using your programming language of choice. And so with the Redshift Data API, I can effectively use any language, so Java, Python, any of the Lambda languages that support AWS Lambda, to build that application to consume the data as well. And that's kind of like starting at the top in terms of consuming the data. But then the idea of, okay, we still have to prepare the data. We have to load it from a source. We have to be able to do some kind of transformations. And we see this popular growth of not just AWS Glue, but particularly Glue Studio. So with Glue Studio, and Shruti will go through a demonstration of this, it's a visual environment to create complex data pipelines or simple data pipelines, but in a visual representation. And behind the scenes, it builds the code for you. So if you need to go in and modify the code, or you want to start in code, that's fine. But building upon our idea of democratizing access to the data, we want to be able to have that visual environment where they don't have to write the code, right? They can just create the data pipeline and then automate that through ingestion. But then also this idea of not just the data scientist using Amazon SageMaker to build their models, but being able to leverage features like Redshift machine learning, where through SQL, I can do create model and invoke the model and run the machine learning model without having to export data into a tool like SageMaker, for example, or into a different data format that SageMaker can consume. But the idea, instead of like walking through this, is to say, okay, and what we're trying to represent on that sort of cards on the right is like, this becomes an iterative process. And so if there's no instances to manage, I have serverless ingestion through AWS Glue, serverless Amazon Redshift, and then serverless BI deployments through QuickSight, right? I can rapidly iterate and create these data products very quickly and have non-technical users, non-coders in this kind of low-code or no-code environment to be able to create these data products and get more insights to data. But then just thinking about machine learning is oftentimes you think about features like Redshift ML, delivering SQL to be able to create the models. But there's also a lot of powerful capabilities in Amazon QuickSight, which, yes, is our business intelligence tool that provides reporting and dashboarding, and it's a rich API for embedding in your applications. But there's also a component of machine learning built directly into QuickSight. And so building upon democratizing access to the data, being able to automatically generate insights from that data and looking at auto narrations or forecasting, ML predictions, and then we'll show, hopefully, Shruti will be able to show QuickSight Q, which will then allow this natural language query. So built upon a deep learning model as part of QuickSight, but again, moving away from the dashboards and thinking about the type of users we can now give access to data by just asking a question. So that kind of sets up like the kind of a high-level view in terms of democratizing access to data. But next, I'm going to hand it over to Shruti, who's going to do a demonstration to actually show how quickly and simple this is to set up when thinking about giving access to data to any number of users.
Amazing. Thank you so much, Greg, for that. Okay. So Today, for the demonstration, right, we are going to talk about a simple use case, right? We're going to talk about an event management company wherein we have three personas. We have our data engineer, Miguel, we have our data analyst, Jordan, and we have our data scientist, Ravi. And it's a simple workflow. You have your data sitting in S3. You want to, not just get it migrated into your data warehouse, but to run visualization on top of it. And beyond that, use this data to predict sales, do predictive analysis on top of that, right? So, simple use case. The key thing about this demonstration is everything is built on top of a serverless platform, right? Like from Glue Studio to Redshift to QuickSight to our Redshift ML, you don't have to worry about provisioning anything. You don't have to worry about maintaining anything, right? You worry about your business use case and building analytics on top of that. So with that, let's take a look at the actual, and wow, it's something else. Give me 1 second. It did not replicate. Can everybody see it? I'm so sorry about this. It's not showing. I did not do anything. Yesterday when we tried it out, it was mirrored. So where is that?
Display is right there. Go to arrangement. And then go to mirror displays.
Sorry about that. Few technical glitches. Okay. So for the first use case, right, which we were talking about, our data engineer. One of the, I assume many of you are AWS customers and AWS analytics customers. So one of the common use cases that we encounter is migrating our data from S3 to Redshift, right? And today for that, you have to worry about inferring the data manually. You have to worry about building transformation code to be able to change different data types, as well as migrating the data from one place to another to utilize, copy command, etc. So just while discussing this, we spoke about 3 different types of code or code pipelines that you have to build to address these use cases. Now you can do it directly using Glue Studio. Glue Studio, as you can see, we have our source of an S3 bucket, which it points to like ticket purchase history. You have a destination of something that we basically went in and we crawled the existing tables within Redshift, and with the catalog, we are just pointing it to the Redshift catalog, which is pointing to the same table, ticket purchased history. And just like that, from a source to destination, we are able to load data using Glue Studio. Now, one of the things that you can do as part of this mechanism as well is a transformation element of it. So let's take a look at one transformation example. Over here, we have a purchase history, one of the columns, and when we inferred this column, it came up as a varchar. Now, of course, for us to be able to run analytics on top of it, we need it to be like an integer or a double or something. So over here, I just need to do is drop down and change it to a double, run the code, and that's it. The Glue Studio, just like that, is able to take my data from S3, change it, migrate it to Redshift, and do data transformations as part of it, right? Like everything that we were able to do, we did not have to write any code associated with it, which previously would have been at least 3 sets of codes minimum. Now let's say all of this data is migrated. We move on to our next persona, which is our analyst. All of this data is migrated into Redshift. Our analyst wants to make sure that, hey, is everything running as expected? Do I have all of my data correct? For this, what they are doing is, on top of Redshift, we have something called as a query editor. This query editor is built in within the platform itself. So previously, for a deploy a platform, maybe install something like a SQL Workbench on your laptop, install different drivers, none of that. Today, they can take it, go and write a simple SQL query and execute against it. Now over here, it's the revenue data, right? The analyst wants to make sure the revenue data that all of the data that got migrated over, can I analyze it and see it properly or not? And as you can see, just like that, it comes up. And the analyst is sure, okay, whatever the data that's been migrated into Redshift is how I expect it to be. Now this is one way of analyzing the data. The second way is building a dashboard around it. So beyond that, to visualize the data, our analyst went in and built a neat QuickSight dashboard. As you can see, fake names, by the way. This is the sports analytics data. We see the football games, the basketball games, all the different teams, how they are doing. And as we can see, the Washington football team is doing probably really good, right? Home teams, all the revenue that we are generating for the football is generally good for the Washington team. Now this is great. The analyst can basically take this report as it or dashboard as it and share it with their marketing team, share it with the executives. Not all the executives are tech savvy, right? This is where the power of QuickSight Q comes into picture, what Greg was talking about. So for QuickSight Q, our marketing team is interested in one simple thing. Okay, which are the games that did not do so well? Let me know which are the games that performed poor. And what they do is they write a simple natural language processing text. Show me host with ticket sales less than 200K of football by month. And what Q does at the back end is it takes this natural language text and it converts it into a query. As you can see, it's connecting it back to the attributes and it provides it an information in a chat. And what the executives can do is if they want to visualize this data in a different format, click, can see it. As you can see over here, we see that the September football games are not doing this great. Maybe start of the season, maybe the marketing campaigns did not perform really well, maybe there were not as many people who showed up for the game. But these are the kind of insights and data which is important for our business executives to understand their business and make better business decisions. Now, everything that we did so far is great, but all of this was looking backwards, right? We looked at the historical aspect of the data, our historical data, which is amazing. But what's important for our customers and our businesses today is what is going to be my sales in the future? This is where the power of Redshift ML comes into picture. Now, let's talk about our third persona, our data scientist, Ravi. All of this data is great, but our data scientist, Ravi, over here is trying to understand what is my sales revenue going to be in future, right? This is what he's interested in. What he can do is he comes into Redshift and just using simple SQL command, he creates a Redshift model, right? He can create an ML model. The beauty of this is all of this done using SQL within Redshift. What Redshift does is at the back, it goes in and it connects with SageMaker. It creates that model on its own. Now, in the past, what our data scientists would have need to do is take all of this data from the data warehouse, load it into a special AI/ML tool, create the model over there, run an inference on it, and pay a ton of money as well, right? Because as you know, in the past, by default, the costs are 10 to 15% to create the model, but the 85 to 90% of the costs are actually associated with the inference of the data. So over here, he created a simple model, right, where he's created a new table, a new column called predicted price revenue. And using this model, he can actually create and using the data, as a training set, he's able to generate data with respect to what are my predicted revenue going to look like. And the beauty of this is when he runs an inference for this data, all of that is free. With Redshift ML, you don't have to pay for the inference of the data. So he can run that query unlimited time. So let's see what the data looks like. As you can see, for this, okay, as you can't see, give me 1 second. Did it come up? Okay, yep. So as you can see, over there, when we're looking at our historical data, September was bad. But when we are looking at the data forward-looking, it actually says for the next year, your October game's actually not going to be that great. It's actually showing us a list of home team games wherein the October revenue is going to be less than 200K. Now, this is additional set of information that we can now take to our executives, wherein now they can start making smarter business decisions, not just based on their historical data, but in your forward-looking data as well. So what you saw from the demonstration was that it's migrate data from source to destination, analyze the data, run predictive analysis on it, and do all of that on a serverless environment without having to write any code on top of that. So you saw the theory of it, but with that, I'd like to pass on the baton to our customer, Clay, who will actually talk about the real-life implementation. With that, Clay.
Thanks, Shruti. Hi, everyone. My name is Clay Martin. I'm a senior data scientist at JobCase. JobCase is an online community dedicated to empowering the world's workers. We're also the third largest destination for job search in the United States. JobCasers, our members, are truck drivers, warehouse workers, cashiers, and nurses. They're the frontline workers that provide the goods and services that we all rely on every day. And it's our job to make sure that they have access to the tools, the information, and the community that they need to find their next great career opportunity. So job recommendation is naturally central to everything that we do. In this talk, we're going to look at democratizing access to data and machine learning across your organization. We'll begin with a simple question. Why do it? What's so great about democratization? We'll argue that if you care about scaling your data sets and you care about extracting as much value from those data sets as possible, then you should also care about democratizing those data sets. We'll then look at why it's so hard. What are the barriers to democratization? We'll see that data scale and data location are the two biggest barriers to democratizing access to data. We'll then see how Redshift and Redshift ML helps us overcome those barriers, and in particular, how Redshift ML helps us solve the dreaded and ubiquitous data model co-location problem. Finally, we'll look at a use case, a job case use case. We'll see how Redshift ML has transformed how we think about job recommendation job case, and along the way, we will see how you can build a recommender system from scratch without leaving Amazon Redshift. Okay, so when you go to a technology conference like reInvent, there are a lot of breakout sessions. There's a plethora of breakout sessions on topics around how to scale your data systems. Right? Things like how do you compress and store data efficiently? How do you manage access to data, to ensure integrity and security? How do you move data across networks? And all of these breakout sessions presume that achieving scale in your data systems is a good thing, a worthwhile objective. And of course, they're right, it is. You should definitely achieve scale in your data systems. But then we have breakout sessions like this one on topics around democratizing access to data. And the implication seems to be that these are separate concerns, right? Independent or orthogonal at best. I would like to just take a second to disabuse you of that misconception, because at JobCase, we don't see scaling and democratization as separate concerns. We see them as two sides of the same coin. Of course, there is a dimension along which we scale our data sets that's measured in terms of terabytes of data and billions of rows in a table, the sort of traditional big data metrics. But there's another dimension along which we scale that's measured in terms of the number of people in an organization that have access to the tools that they need to extract the value that is latent in the data that we already have. Right, so democratization is about scaling along that dimension. And if you don't scale along that dimension, you're like a mining company that knows that there's gold in the hills, but you can't get to it because your miners don't have the pickaxes and the backhoes and the earth-moving equipment they need to extract the gold. So my message is, don't leave the gold in the hills. Don't leave the value in your data sets. Get the value out. Get the gold out. Democratize your data. Okay, so why is it so hard? Why haven't we all done this already? So barrier the first to democratizing data is just the sheer scale of the data that we are logging, right? At JobCase, over the last 8+ years, Every day, we have sent millions of emails. We have generated millions of arrivals from those emails. We have generated millions of job search results from those arrivals. So that's every day, over 8 years, millions of emails, millions of arrivals, millions of job search results, all stored in highly compressed, highly optimized Amazon Redshift tables. It's terabytes of data, billions of rows across dozens of Redshift tables. On the other hand, the data structures that our data analysts and our data scientists are most comfortable with using, structures like Pandas data frames and R data frames, like they just inherently don't scale to these sizes. I mean, if you've ever seen a Pandas data frame with a terabyte of data in it, then I don't run away, I guess, or tell me about it. I've never seen one. I'd love to see that. The point is, there's just a fundamental disconnect between the amount of data that we can store efficiently and the amount of data that our analysts can analyze with the traditional kind of data scientific data structures that they're most comfortable with. So I just want to apologize in advance if this diagram is triggering anyone. This diagram represents the pernicious, the ubiquitous, the until now unsolvable data model co-location problem. This is also like a traditional data science pipeline at job case before we adopted Redshift ML. So, the data model co-location problem is like Fermat's last theorem. It's very easy to state and very difficult to solve. But it is this. Basically, you have your data somewhere, like a centralized Amazon Redshift data warehouse, and then you have your models somewhere else, right? It could be on a separate EC2 instance, or worst case scenario, it could be on a local machine. That's a worst case scenario, but it's unfortunately not that uncommon. And so in order to leverage the value that is presumably embedded in your models, you have to move your data from your warehouse to your models and then back again. So if it's in a Redshift database, you have to write your data to an S3 bucket, you have to read it into an EC2 instance, you have to load it into whatever data structure your models need, you have to call a predict method on your model to generate one column of predictions. You have to then write those predictions to an S3 bucket and then read them back into your Amazon Redshift data warehouse. Does that sound familiar to anyone? Yeah, I hope so. I hope not. And so you're doing all of this data movement to generate one column of predictions, right? And presumably that's a valuable column. I mean, that's why we hire data scientists in the first place, to build all these models to generate predictions, right? Nonetheless, over the last 8 years or so at JobCase, we've measured the marginal value of those predictions versus the marginal cost of laying and maintaining all of this data pipeline. And we've discovered that oftentimes it's not, the marginal value is not greater than the marginal cost. So what do? Right? Well, we don't do that, right? It's like economics 101. If marginal value less than marginal cost, you don't do that. It's irrational. So we fake it, right? We fake it. We come up with some representation of our models that can be encoded directly within our data warehouse, i.e. directly within SQL. Right? We're not going to capture 100% of the value. We might get 80%, maybe 60%. And if this was a one-off, if it was just you and me, we're going to make a model and then we're going to go to lunch and move on with our lives, then that would be one thing. But of course, that's not the way enterprises work. We know that across the enterprise, on the sales team and the traffic team and the marketing team, everyone's faking it, right? Everyone's losing 20% of the value here, 30% there, 40% there, because the data and the models are in different places. Right, so that's a lot of value to give up just because of the dreaded data model co-location problem. Luckily, the people at AWS, it turns out they're pretty smart. I don't know if you noticed this, but they seem pretty smart to me. And they realize that the solution to the data model co-location problem, which just to review is that your data's over here and your model's over here, is that you want to put them in the same place, right? Don't move the data to the models and then back again. Just move the models to the data and then keep them there. That's the solution. So this is what our data science pipelines look like now, right? If you like squint really hard, you can see the differences, right? I'll just give you the answer. The difference is that there aren't any arrows anymore. Like all the arrows are gone because the data and the models are in the same place. They're all in Amazon Redshift, right? And so now the analysts on our traffic team, they can build models that predict the lifetime value of a user. And the analysts on our email team, they can predict the probability that a user is going to click on an email. And the analysts on our sales team can predict the probability that a potential client will become an actual paying customer, right? And they can all do this directly within Amazon Redshift, writing SQL queries, which they can all do, because if they couldn't, then we wouldn't have hired them probably. And so they don't have to fake it anymore, right? And we're not losing any of that value anymore. And so if that's not democratizing data, at the enterprise scale, I don't know what is, honestly. If someone asks you, what does democratization look like, you can say, it looks like a data diagram without any arrows in it. Okay. All right. So how about that use case, that job case use case? So like I said, we're the third largest destination for job search in the United States. That means that we have over 20 million users on any given day that want a job, and they come to us looking for it. So we have to recommend job search content to about 20 million users. That content comes from several places. One of them is a job store. It has about 20 to 30 million active job listings at any given time. That jobs, you can think of it as kind of like, a picture of the US labor market at any point in time, right? It's the help wanted sign in the window. We also recommend companies, about 1 million different companies, right? So if we send you a company email, you click on it, you'll see jobs for that company in your area, hopefully. We also recommend job search terms. You click on one of those emails or one of those push notifications or one of those SMSs, you will go to one of our sites and you will see results that match that search in your area, hopefully, right? So if you do the math in your head or on the back of an envelope, then you'll realize very quickly that we can't score every possible user in every possible job or every possible user in every possible company because there's literally trillions of such combinations. Even if you hand me an Oracle function, a function that perfectly scores every possible item for every possible user, I can't just use it naively because, again, trillions of such combinations, computationally infeasible. Right? So the size of the problem naturally factors the solution into two phases. The first phase is we have to reduce the size of the problem. We have to reduce the candidate set of items that we put in front of, we score for each user to some reasonable size. Maybe 300 items, maybe 500 items, maybe 1,000 items. It's a hyperparameter of the system that you'll have to optimize via A/B testing. I assume that everyone here can do it, and we're not going to talk about that anymore. Once we've done that, though, we can then score the remaining items for each user, and we can do that using Amazon Redshift ML directly within our data warehouse. I guess the last phase is that we profit. Okay, so how do we go from this really big search space to a much more tractable search space? So the people that design recommender systems, they're just like the rest of us, which is to say that they're extremely lazy. And so one of their favorite methods for reducing the search space is collaborative filtering. Right? So in collaborative filtering, we like that because we don't have to know anything about the items that we are recommending. We only have to know about patterns of user item engagement. And if you think about it, it's extremely simple to represent these patterns in something like an Amazon Redshift table. It's a 2-column table. It's a very long table, but it's very narrow. Then you have one column that's just user keys. And then you have the other column that's just the items that those users have engaged with in the past. Right? So imagine that you go to a movie streaming site, right? You see marketing material like this all the time. It says, people who watched Raiders of the Lost Ark also watched Star Wars, right? So think about what they don't need to know to say that, right? Like they don't need to know that Harrison Ford was in both movies. They don't need to know that they're roughly the same genre, I guess. They don't need to know they're both made in the 80s. Maybe Star Wars wasn't, I don't know. I should have picked different movies. But the point is, they don't need to know really anything about those movies except for the fact that people who watch one also watch the other. Same with jobs, right? People who search for cashier jobs, I can tell you, they also search for like front office assistant jobs. They also search for customer service representative jobs. They also search for, sales floor associate jobs. And so, we're going to use a collaborative filtering technique to take that 2-column table, user keys, item keys, and we're going to map that to another table in our data warehouse that has 3 columns, an item, another item, and a score. And that score is going to tell us how similar are these 2 items to one another, right? Similar in terms of distance and some Euclidean space that we have embedded them in, right? Using some technique that we'll talk about in 1 second. We then, once we have that other table, right, we join it back to our original table. And why are we doing all this? Right? To end up with a table where every user is mapped to items that are most similar to the items that they have already engaged with. Right? That's where we get the 300 items, the 500 items, the 1,000 items, whatever that hyperparameter value tends to be. Okay, so there's lots of ways to do this, right? There are classical data mining techniques that you can implement directly within Redshift, and you've been able to do this for hundreds of years at this point. Things like Jakarta distance, cosine similarity, these are computable using traditional SQL queries. You don't even need Redshift ML to do this. And we're going to see how well this works on the next slide. But maybe you want to get fancier. Maybe you want to use classical machine learning techniques like unsupervised learning, collaborative filtering, not collaborative filtering, k-means clustering. You're going to have to leave Redshift for that. You're going to incur all the costs that we already talked about. So, maybe take a minute, take a breath, and think about that before you do it. But maybe you want to get super cutting edge. You want to steal some ideas from natural language processing, right? Because if you think about that table, that user key, that item key table, it's sequential, right? It's kind of like natural language. Natural language is sequential. The users are talking to us. They're saying, I want this, and then I want this, and then I want this. Kind of like when, you talk to your best friend. And so we can take some vector embedding techniques from natural language processing. We can apply it to the items in our user item data set. And the semantic relationship between the items, people who like this, also like this, that's going to show up and where those vectors end up in our metric space. But again, that's not something that is computable within Redshift yet, so I'm just going to leave that there, put a bow on that, and we'll move on. Okay, so like I said, Jacquard distance has been around forever. It's very basic, it's classical at this point. It's also pretty good, right? So I wrote some SQL queries against our actual user item history table using Jacquard distance. And this is what this SQL query returned, right? You've all seen this kind of marketing material all over the internet, right? People who like this also like these things. Well, I'm a data scientist, so, I can tell you, like research scientists, yeah, that's kind of up my alley. If a recruiter came to me and I wasn't happy at job case, and they said, we want you to be a research scientist, I might like that, right? Or what about the next one, warehouse worker? Well, there's material handler, forklift operator. These are literally things that you do in a warehouse, right? So these are pretty good associations, just intuitively. My point being, sometimes you don't need like the shiniest tool in the toolbox, right? Sometimes you can do things that are pretty good directly within your data warehouse, and because you're doing it in Redshift, and because Redshift has like very fast approximate count algorithms like hyperlog log functions, this all gets done blazingly quickly. So sometimes you start with a simple thing, that becomes a benchmark for the more sophisticated things that you want to try later on. Okay, so once we've done that, now we have the 300 items, the 500 items, the 1,000 items, whatever it is. Now we can actually score them. And this is where Redshift ML has really transformed how we think about recommendation and job case. Right? Because now we can do all the feature engineering directly within Redshift. We could have done that before, but what were we doing it for? Just to like leave Redshift and then come back. So we have user-level features like educational attainment, the skills that users have, the years of experience that a user has. We have item-level features like what kind of job is this? What kind of industry is it? What kind of skills does it require? And then we have the user item, the intersection between those two things, right? So what's the similarity score between this item, this job, and other items that that user has engaged with in the past, right? People who watch this movie also watch this movie. How many times has this user searched for this job in the past or clicked on this job in the past? These are all features that we could calculate. And now, once we've done that, we don't have to history bucket onto some separate. No, we can just dump them into a SQL directly within Redshift. So, I'm almost done here. So we've designed all of our features. So now we just have to build a model, which again, we can do directly within Redshift. Of course, the model class that we're going to build depends upon the key performance indicator that we're trying to maximize. Right? So we're trying to maximize engagement, like CTR rate, the probability of a given user clicking on a given email. In that case, we're going to use something like a logistic regression, right? Or a feed-forward neural network with a cross-entropy loss attached at the end, or an extreme gradient boosted model. The point is, we can fit all of these directly within Redshift now. I sound like a broken record, but it bears repeating. We can do all this within Amazon Redshift now. Maybe we want to maximize value percent, whatever that is. Let your business manager tell you what value percent is in this case. It is a real number greater than 0. We can use another feed-forward neural network, extreme gradient boosted model, linear regression, all within Amazon Redshift. All right, in summary. So now we have access to cutting-edge model classes directly within Amazon Redshift. All of this is fittable, trainable, inferenceable, if that's a word, directly within Redshift using SQL queries. We can train models against tens of millions of rows of training data in a matter of hours. If we tell Redshift ahead of time which model class we want to use, like if we say we want you to use a classical logistic regression model, or we want you to use a feed-forward neural network, or we definitely want you to use an extreme gradient boosted model, then it's much faster. But otherwise, it has to search the entire model space, right, and tune the parameters across all those spaces, and then it returns the best model to us. Of course, we don't have to sit there and wait for it to, we can go to lunch and come back, and then it's done, and it's great. And then at inference time, we can perform inference, that is, make predictions against 2 to 3 billion rows of data in a matter of minutes. At the time of writing, it was 15 minutes. I think my coworker, AJ, told me recently that it's more like 10 minutes now. So it just keeps getting better all the time. It's great. We're not incurring any more costs. In fact, we're probably saving money, right? We're doing all this on the infrastructure that we're already paying Amazon for. So that's great, too. And the business managers really want to see this last bullet point, right? We're actually getting a lift in terms of like the KPIs that the business cares about, in terms of higher click-through rates, higher values percent, like in the 5 to 10% range across all of our outbound communications. And then finally, since this is about democratizing data, I'll just say that we're doing this across the organization. So it's not just the recommender system. It's the traffic team, it's the marketing team, it's the sales team. It could theoretically one day be the executive team. So with that, I will hand it back to Greg.
All right, thanks, Clay.
Yeah.
All right, so we're about ready to wrap up. So in terms of next steps, we talked a little bit about the theory up front. We saw a quick demo, then heard an application from Clay about job case. And I guess the encouragement I would have for everyone is give it a try, right? So we had a lot of announcements at reInvent like every year, thinking about democratizing access to data. What are some real challenges in your organization, whether it's ingesting data, preparing it, loading it, visualizing it, and try it out, right? And that's the great thing is, in a matter of minutes, if not hours, the worst case, maybe 10 or 15 US dollars, like you can actually take a set of data, see what type of analysis you can get out of it and the value, and then repeat that over and over again, right? So thinking about how quickly you can test it out, I think is really transformational in terms of taking some of this theory into how it can help your business. Now, some other sessions, I think in terms of on-demand content, Swami's keynote, I think is really a key recommendation I would have for everyone to take a look at how you bring together other machine learning and analytics services to solve better problems for a different set of customers, as well as Rahul Pathak's leadership session around analytics to think more about practical applications and other new capabilities that AWS keeps adding. This discussed a couple other sessions in terms of ANT 301 and 215. You can either catch live here in Las Vegas or on demand. So thanks everyone for coming. I know we've got a few minutes for questions. I think if you want to either meet us on the side or if you want to come up and talk to us, but please encourage you everyone to fill out your feedback on our session today. And we'd love to hear how we can make future sessions better. But thanks for your time. If there's any questions, either myself, Shruti, or Clay are happy to answer them.